Welcome, dear students. So this is the second lecture on structural dynamics, C6102. So in the first lecture we have seen what are the essential characteristics of a dynamic system and what are the basic components of a dynamic model and what are the various methods of modeling actual structures to develop its dynamic model, namely the lumped mass system and the generalized displacement procedure. So in this lecture we will first see how to formulate the equation of motion or equilibrium equation of a dynamic system, and then we will study about the different types of vibrations, and then we will study analysis of undamped vibration and damped vibration, and after that we'll go for some methods of finding equivalent stiffness of combination of springs and why those combined springs are necessary. That also will be clear once we take up that issue, and then of course we'll solve a few problems. So first thing is the formulation of equation of motion. So for equation of motion formulation, we already know that from the first lecture we have seen that in a dynamic system the presence of inertia is one of the essential characteristics of a dynamic system, right? So presence of inertia force. Now you all know that the job of inertia is to preserve its state of rest or state of motion, alright? And therefore, as per Newton's second law, since inertia force is present, therefore Newton's second law is involved, and as per Newton's second law, you know that the net force acting on a system, what is meant by net force? Net force means the resultant force of all the resultant of all the forces acting on a system, that is equal to the inertia force, right? Or simply the rate of change of momentum. This is my statement of Newton's second law, right? So Newton's second law of motion. So the same Newton's second law is also applicable for a dynamic system, right? Now let us consider a very simple single degree freedom system. So we already have seen single degree freedom system earlier. So I will have a block of mass, right? And I will have a spring. See, I have a spring, and I will have also a damper or dashpot. Okay, and this is a very simple single degree freedom system. All right. Now, in order to start vibration of the system, suppose I pull this system, the mass, by an external dynamic load. Okay, for suppose I pull it by a force, say F. So what will happen? The mass will be displaced, right? The mass is displaced and the spring will be extended, right? It will get extended and similarly my damper also, there will be some relative displacement between the piston and the cylinder. Say this is my cylinder and this is my piston. Now piston has moved compared to the position at rest. Okay. Now therefore when the spring is extended, the job of spring is to restore the mass to its original position. So the spring will pull the mass back, right? And therefore if I draw the free body diagram of the mass, suppose this is my mass, so the spring will exert, the spring will exert a force towards the right side, right? And also for the time being, let me just tell you that due to this relative displacement between the piston and the cylinder, there will be some frictional force developed, okay? And that frictional force will also oppose the motion of the block. Therefore that will be equivalent to another force in the towards the right hand side. All right, and we already have this dynamic force in the opposite direction, which I call as Ft, right? Say Ft. Therefore what is my net force acting on the system? Say F net. Net force is the resultant force, and if I take the left hand side direction as positive, because I am giving a positive deformation of the mass, I am assuming. Of course that doesn't matter, you can take the right hand side forces also positive, ultimately we will get the same result. Say I am giving a deformation of say x, okay, which is of course again a function of time because the system is dynamic. Okay, so what will be my net force? My net force will be Ft, this is positive force, minus this spring force, I will call it say Fs, and this is my damper force, I will call it Fd, okay, for the time being. So Ft minus Fs minus Fd. So this is my net force acting on the mass, and since my net force is equal to the inertia force, therefore this must be equal to the inertia force. And what is inertia force? Inertia force, I know that it is mass times the acceleration. If x is the deformation, I know that second order time derivative of x will give me the acceleration, and therefore I am writing it as x double dot. In the last class we saw that a dot represents the differentiation with respect to time, and the number of dot represents the order of differentiation. So since it is second order differential, therefore I am using 2 dots. Therefore this F net is equal to mass times the acceleration. So what I can write is that this F net force is equal and opposite to the inertia force, right? And in other words, what I can write F net minus mass times the acceleration is 0. Okay, so what does it mean? It means that this inertia force has developed due to the acceleration present, as we have understood in the last class, and this job of this inertia force is just to oppose the net force. So this will be acting in a direction opposite to the net force, right? And therefore, in addition to these 3 forces, Ft, Fs and Fd, the resultant is my net force. I will also have another force. Which is my inertia force, okay? And this inertia force, I will draw it by a dotted line, say. I'll draw it by a dotted line, dotted arrowhead, and its value I will write as, say, Fi, and this Fi is nothing but m times the acceleration. Okay, so this gives me actually, in a nutshell, the equation of motion of the system. And this phenomenon, that the inertia force develops and it acts at a direction opposite to the direction of the acceleration. So its job is to oppose the acceleration. Because it is inertia, it will oppose the acceleration, or the state of motion will be opposed so that it can preserve the original state of motion. That's why it will oppose the acceleration. And this principle, that inertia force will act in a direction opposite to the direction of acceleration, in addition to all other forces, is called D'Alembert's principle. All right. Sorry. It is called D'Alembert's principle. So by using D'Alembert's principle, we can easily write the equation of motion. All right. What does it say? It says that inertia force opposes the acceleration. And the value of inertia force is given by Newton's second law, which is mass times the acceleration. Okay. So finally, what we get, the equation of motion as F net, the net force, minus Fi, the inertia force, is 0. So when using D'Alembert's principle, it becomes easy to write down the equation of motion, because I need to just identify all the forces due to the spring, due to the dashpot and the external dynamic load, and I have to put another force, inertia force, in a direction opposite to the direction of acceleration. So this is called D'Alembert's principle. Okay. Now let us find out the values of the spring and damper force so that I can write down the full equation of motion. Now you see, if I have, I know that it is a linear spring because we are discussing only linear dynamics. So a spring is characterized by what? A spring is characterized by its stiffness, you all know. So spring force will be equal to, which I have denoted as Fs, will be given by the stiffness times the deformation, K times X, where K is my stiffness, that is load per unit deformation. And the damping force or the damper force is usually taken as proportional to the velocity of the mass. Okay, so Fd is proportional to velocity. What is my velocity? Velocity is x dot dx dt, right? Usually we call that the damper force is proportional to velocity to the power some factor n, and people have done many experiments, okay, many experiments where they have measured the damping force, say Fd, and they have plotted against the velocity, and for different systems different types of distributions are obtained, and usually for structural dynamic purposes what we find is that the damper force is usually linearly proportional to the velocity, and when this is so we call it viscous damping. Okay, we call it viscous damping. And usually in structural dynamic problems we assume that our damping is viscous. We call it viscous damping. And in that case my damping force will be Fd will be proportional to velocity to the power 1, and therefore we write it as some constant into velocity. This constant C is called damping coefficient. Okay, and usually we write near the damper this coefficient, value of this coefficient C. Okay, so if I put these values of spring force and damper force in my original equation of motion, then what I will get? I will get Ft minus Fs, which is K times X, minus Fd, which is C times X dot, is equal to mx double dot, right? Now by transposing the terms, by transposing the terms, what we'll get from here, I will get mx double dot plus cx dot plus kx equal to the external dynamic load Ft. Okay, and this gives me the equation of motion of a single degree freedom system. All right, so this is my equation of motion of an SDF system. Equation of motion. All right. Well, we also have another method of finding the equation of motion, or deriving the equation of motion, or formulating the equation of motion, and that is known as principle of virtual work. You are already familiar with this principle. In principle of virtual work, what we do, we apply a virtual displacement to any system, and we find out the work done by various forces over this virtual displacement, and we find that the virtual work done by the system of forces, the sum of that is 0 in a conservative system, and that is what is the principle of virtual work. So let us apply this principle to our dynamic system, spring mass dashpot system. Now I have this mass and I am applying a virtual displacement of say delta u. This delta just indicates that it is a virtual quantity. I am applying a virtual displacement of delta u in the positive direction. Okay, and therefore what are my work done by the various forces? The work done by the external dynamic load over this virtual displacement is given by Ft times delta u, right? Then I have another virtual work done, which is equal to the virtual work done by the spring force, and that is given by minus Fs times delta u. Why minus? Because I know that the virtual work done by this force is opposite in the direction, opposite to the direction of the virtual displacement. That's why it is negative. Similarly, the work done, virtual work done by damper force is Fd times delta u, negative. Okay, and this sum of all these virtual work done must be equal to the virtual work done by the inertia force. Okay, so since I have inertia force which is equal to Fi times delta u, which is my virtual work done by the inertia force. Therefore, as per the principle of virtual work, what I will get? I will get Ft times delta u minus Fs times delta u minus Fd times delta u. This total work done must be equal and opposite to the work done by the inertia force, virtual work done by the inertia force. So Fi times delta u, and therefore once again I get that by transposing Ft times delta u will be equal to Fi plus Fs, Fd plus Fs times delta u, right? and by cancelling my delta u, I again get Fi plus Fd plus Fs spring force must be equal to the external dynamic force. Okay, and putting the value of inertia, damper and spring force, I will again get back the same equation. Inertia is given by mu double dot now, because my displacement is u, that's why virtual displacement is delta u now. So plus c times u dot, if my damping coefficient is c and if my spring coefficient is k, then I have k times u equal to Ft. So I again get back the same equation which we had already got. Alright, so this is the equation of motion of a single degree freedom system when acted upon by an external dynamic load. Alright, now principle of virtual work is not so advantageous for such a simple system, but if the dynamic system itself is more complicated, there are different degrees of freedom and their motions are in different planes, then principle of virtual work becomes much more convenient to find out the equation of motion. The reason is, if I consider the forces, I need to consider them as vectors, but you know that work is a scalar quantity, so by applying principle of virtual work we can add them algebraically. All the virtual works can be added algebraically instead of vectorial addition. So in that case, in a complicated system, the application of principle of virtual work becomes more convenient to find out the equation of motion. Alright, so this is how we can find out the equation of motion of a single degree freedom system. Now let us see the types of vibrations. Now the types of vibrations, we can basically divide the vibrations into two types. One is free vibration, the other is forced vibration. Now while deriving the equation of motion, we have always considered an external dynamic load for simplicity. Okay, but in reality I may not have any external dynamic load during the vibration. For example, suppose I just pull this mass by some amount and then release it. Once you release, the mass will start vibrating, as you know. Okay, and during that vibration phase, therefore there is no external dynamic load acting. Okay, in that case what I can write is that my external dynamic load is not present, so Ft is 0, and therefore we will call it a free vibration. And if there is some dynamic load acting during the vibration, then of course this Ft is a non-zero quantity, and such vibrations are called forced vibration. So we have two types of vibrations. Basically, one is free and the other is forced. So in that case, if I have a free vibration of a single degree of freedom system, what will be my equation of motion? My equation of motion will be, say, mu double dot plus cu dot plus ku will be equal to 0 now, because Ft is 0 here. Okay, so this is what is called free vibration, and the equation of motion of a free vibration is this. And for forced vibration, we have already seen that the right hand side will be replaced by Ft. Okay, So I will have, say, mu double dot plus cu dot plus ku equal to some dynamic load Ft. Alright. Now, whether it is free or forced, in some cases I may not consider the energy dissipation term. If the energy dissipation is very, very small, say for many civil engineering structures like buildings where it vibrates, the loss of energy is very, very small. Okay, and in that case I may take that this C is nearly 0, and in that case what I will have, I will just remove this term, and in that case I will have, in case of undamped vibration, I will have mu double dot plus ku equal to 0. This is called undamped vibration because my damping term is 0 here. No damping, no dissipation of energy is taking place. So C is 0. And if it is damped, then C is not equal to 0. So I will have this equation. Okay, I will have this whole equation. Let me erase this. So I will have mu double dot plus cu dot plus ku equal to 0 because it is free. And similarly here, in case of forced vibration, if it is damped, then I will have all the terms that we have seen already, mu double dot plus cu dot plus ku equal to Ft. If my force is periodic, then I will have a periodic function in place of Ft, and if it is undamped, then I will have mu double dot plus ku equal to Ft. Okay, so depending on the presence or absence of external dynamic load during the vibration, and depending on the presence or absence of damping in the system, I can have free and forced vibration, and both free and forced vibrations can be either damped or undamped. I have also written the corresponding equations of motion in every case. Okay, so these are my major types of vibrations we will discuss in this course. All right. Well, let us analyze the undamped free vibration. Let us understand the physics of undamped free vibration. But before going to analysis, let me show you one small video. You see here an undamped free vibration is shown where the displacement of this mass is shown as the vertical motion of this bob, and this is related to the circular motion of another body with a radius r. Usually we take this r as unity, and we see that the motion is repeated after a full rotation along the circle, which has a period of twice pi. Okay, so therefore we also see here that the motion of the particle itself, say it is the mass connected to a spring, the motion of that mass itself can be expressed by a simple harmonic function like sine function, or if I start from here, it will be a cosine function. Okay, so after looking at this video, the analysis of undamped free vibration will be more easily understood. For that, let us go back to our presentation. Suppose I have a spring mass dashpot system which has mass m and a spring stiffness k. Since it is undamped vibration, therefore there is no damper, damping coefficient is 0, and also since it is free vibration, there is no external dynamic load acting during the vibration. Just to start the vibration, I pull the mass by an amount of initial displacement x naught, so that x at time t equal to 0 is x naught. Okay, and because there is no damper, therefore there is no energy dissipation or energy loss during the whole vibration, and therefore my total energy during the vibration must be remaining constant. So I can say that total energy Te is constant. Okay. Now if at any time the displacement is x and velocity is x dot, then what is my potential energy? In that instant, potential energy or the potential energy will be given by the strain energy stored in the system, and that will be equal to half into force, spring force, times the displacement, which is x. And I already know that spring force is k times x, and therefore it will be half k x square, right? Remember, x is a time variable, it's a function of time. Similarly, kinetic energy at time t will be equal to how much? Half times mass times the velocity square, and velocity is x dot, so x dot square. So therefore, what is my total energy? So total energy will be given by, at time t, my total energy is given by sum of this potential and kinetic energy. So I have half times k x square plus half times m x dot square. Okay, so this is my total energy at time t. Now I know that just at the start of vibration at time t equal to 0, there is only displacement, which is x naught. Okay, so at time t equal to 0, at t equal to 0, what is my total energy? Total energy must be the only potential energy, because there is no velocity, so no kinetic energy at that point. So that will be equal to k x half times k into x naught square, right? And this energy must be same as this total energy at any instant, because my total energy is remaining constant. Therefore, based on this consideration, what I can write? I can write that this energy at time t must be equal to energy at time t equal to 0. So half kx square plus half mx dot square is equal to half of k x naught square, right? Now I can cancel half from each term. Okay, and then let me divide both the sides by kx naught square. All right, so if I divide both the terms by kx naught square, what I will get from here? I will get, this will give me, here I will get x by x naught whole square, right? And here what I'll get x dot naught by m will be here and k will be here, right? I will have the k here, I'll have k here, and I'll have x naught. This is square, this is square, and this will be equal to, in the right hand side I will have 1. So this I can simply write as x by x naught whole square plus x dot naught I'm sorry, this naught will not be here, no? But this is x dot only. So x dot divided by x naught, and here I can write this as root over k by m whole thing squared, right? And this is equal to 1. Now you see this term, this first term is related, it is a ratio of x by x naught, and therefore this is a ratio of displacement, so this quantity is proportional to my potential energy. Alright, and this quantity is related to my kinetic energy because it is proportional to square of velocity. And what we have seen is that this term plus this term gives me 1. Therefore, this is an equation of a circle having a radius of 1, where in this direction, x direction, I can put this potential energy term, okay, which is nothing but my this term x by x naught. And in y direction I can plot this kinetic energy term, which is nothing but x dot by root over k by m into x naught. Okay, now if I plot this equation shows me that it will be a circle having unit radius. Now at the very beginning my vibration starts here, you see, because this quantity is 1, that means x is equal to x naught. So this is my time t equal to 0. Okay, and as the time moves, then what happens, this point moves towards point B, and at B what is happening, my potential energy terms becomes 0 and the kinetic energy terms becomes 1. That means this term becomes 1. So at that point my kinetic energy is maximum, alright, and the potential energy is 0. And therefore, since kinetic energy is maximum, it has highest velocity, and since the mass is having inertia, therefore it cannot stop here, it moves again towards this side. And that means in this side what is happening, my displacement is becoming negative because this potential energy terms is becoming negative. That means the spring is this, here my spring was displaced by maximum amount, by an amount of x naught as here. Okay, then as the vibration goes on from this point to this point, what is happening, the spring is pulling the mass, So at this point the potential energy is 0. That means it has come to its mean position of rest. There is no deformation of the spring, but velocity is maximum, and therefore after this point the spring is compressed, the mass is moving in the opposite direction. That's why potential energy has become negative now. X has become negative, so that x by x naught is negative, and gradually that compression is increasing and increasing and increasing, and thereby here it again the maximum compression of the spring takes place. So potential energy is again maximum, but now the inertia will be in the opposite direction, so it will again start moving. The spring will try to extend again to push the mass back towards its mean position of rest again, alright, where the displacement is 0 now, but the velocity is in the opposite direction, and therefore again it is having peak kinetic energy, so it cannot stop, so it will again come back to its disposition, initial position of motion, and this cycle will continue. So that's how the preservation of energy drives the vibration. So kinetic energy, the potential energy is completely converted into kinetic energy, then kinetic energy is completely converted to potential energy, and that cycle continues again and again and again. Because there is no energy loss, the vibration continues. Okay, and that's how we can express the physics of the undamped free vibration. All right, physics of undamped free vibration. So this is my equation showing that this is a part of circular path having unit radius. So this is similar to the video we have seen earlier, where the point is moving in a circular path and the mass is moving in a sinusoidal motion. Okay, all right. Now in the video we have seen that the motion of the mass can be expressed by a harmonic function. Okay, and therefore coming back to here, we have seen that the motion is repeated over a full circular motion, which has a period of twice pi, right? The mass, this point moves by an angle of twice pi, and the time taken for this complete cycle of motion, this completes one cycle of motion, and the time taken by the mass to complete this one cycle of motion is called time period of motion. Okay, so we will call it time period of motion, and it is denoted by capital T. Capital T is called time period, or simply period of motion. Time period. Okay, so this is the time when one cycle of motion is completed. So time required to complete one cycle of motion. So this is called time period. All right. Now since we have seen that the motion of the mass can be expressed by harmonic motion, therefore let me assume that my x, which is a function of time, can be expressed by sum of harmonic terms, say a cos omega t plus b sin omega t, where this omega is given by the circular speed of this point, and that will be given by what? It will be obviously given by twice pi by t, right? Omega is twice pi by t, because with time t the complete angular motion completed is twice pi, so per unit time the angular velocity is twice pi by t, and therefore I write xt equal to a cos omega t plus b sin omega t. Now these constants of integration a and b can be expressed by, can be obtained by using initial conditions. Now what are my initial conditions? I had assumed at time t equal to 0 my deformation x was x naught and the velocity was 0. I had assumed velocity to be 0. Alright, therefore if I differentiate this x with respect to time, then what is x dot? X dot is minus a omega sin omega t plus b omega cos omega t, right? Differentiation of sine is cos and cosine is minus sine. So I have got this, and therefore at time t equal to 0, if I put time t equal to 0, then my left hand side is, there is no velocity, so I have got 0 in the left hand side, so velocity is 0, and here sine 0 is 0, so this term will not be there, cos 0 is 1, so I will have the velocity at time t equal to 0 equal to 0. Then from the right hand side we have seen that b omega is 0, because sine 0 is anyway 0, therefore b must be 0, and therefore xt is a cos omega t. And I know that at time t equal to 0 my x is x naught, and therefore if I put x equal t equal to 0 now, I get x naught is equal to a. Okay, so therefore my x is nothing but x naught cos omega t, right? X naught cos omega t. And hence what is my x dot naught or x dot? What is my x dot? X dot is, I'll differentiate this, so I will get x naught omega minus x naught omega sine omega t, right? Now if I put these two values in this equation, what shall I get? Let me write it here itself so that I don't need to change the page. Now if I put these values here, let me put this value and this value in this equation, then what I'll get? I'll get, in place of x naught x, I will write x naught cos omega t by x naught whole square plus what I'll get, x dot. What is x dot? X dot is minus x naught omega sine omega t by root over k by m into x naught whole square is equal to 1. So here you see this x0 and x0 goes, this x0 and x0 goes, and therefore because this is square term, I get from here that cos square omega t plus this becomes k by m. So if I take it up, then it becomes let me write it like this: omega by root over k by m whole square into sine square omega t must be equal to 1. Now I know that cos square omega t plus sine square omega t is 1, therefore this quantity must be 1, and therefore I get omega square is k by m, or omega is root over k by m. Alright, so this is a very important equation. This is called natural frequency of vibration. This is called natural frequency. Natural frequency of vibration. And this gives me what was my omega originally? Omega is twice pi by t, and that is equal to root over k by m. This we have seen. Why we call it natural frequency? Because this is the number of times the motion takes place per unit second, right? Number of times the cycle is completed. That's why it is called frequency, and it is called natural frequency because its value depends on the natural vibrational properties of the system, which is k and m. So it is a system property, inherent system property, which is the stiffness and mass, and the stiffness and mass, which are the inherent property of the system, will govern at what frequency it will vibrate under free vibration, and that's why it is called natural frequency. So natural frequency is given by root over k by m, and it is an inherent system property, and therefore the word natural is used. All right, and from here we can also find what is t. What will be t from here? Natural time period. I called it as time period, but we have seen that it is again a natural property of the system. So natural time period is given by twice pi by this, so I will get twice pi twice pi into root over m by k. This will be my natural period. Alright, from here I can find it. Let me write it a little more beautifully. So twice pi root over m by k. So this is another equation we have got today. So t is twice pi m by k. So if I know time period, I can find frequency. If I know frequency, I can find time period. And for frequency, knowing frequency, I need to know the stiffness and mass of the system. And that's why it is an inherent property of the system, and that's why we call it natural frequency. So finding natural frequency is one of the very important tasks of finding the dynamic properties of a system. That is the first dynamic property that we must know to analyze this system, because you see my motion is dependent on this natural frequency, okay, on this natural frequency omega. Sometimes we also write a subscript n in place of after the omega, okay. Sometimes we also write natural frequency as omega n, okay. So I can also write omega n as root over k by m. So whenever you see that omega is root over k by m, automatically you come to know that it must be natural frequency. Whether we write the subscript n or not, it obviously indicates that it is a natural frequency of the system. Alright, so with this I think I should stop analyzing the undamped free vibration, okay. In the next class we will see how to analyze damped free vibration. Right.